Nuclear stability. Here I'm going to look at what conditions lead to stable nuclei. I'm going to plot a graph of the number of neutrons, n, against the number of protons, z. First I'm going to add this line, which shows where the number of neutrons equals the number of protons. The first isotope I'll add to the graph is neon 20. This has 10 protons and 20 minus 10, which is 10 neutrons, and it appears on this line. If we divide the number of neutrons by the number of protons, for this isotope we get 1. Next I'll add iron 56. This has 26 protons and 56 minus 26, which is 30 neutrons, and appears here. If we again divide the number of neutrons by the number of protons, we now get 1.15. The next isotope I'll look at is silver 107. This has 47 protons and 107 minus 47, which is 60 neutrons, and appears here. Again, doing number of neutrons divided by number of protons, we've now moved up to 1.28. Finally, up here we have tungsten 184. This has 74 protons and 184 minus 74, which is 110 neutrons. It appears here, and doing the number of neutrons divided by the number of protons gives us now 1.49. If we join these and other stable isotopes, it gives a line something like this. So we see that as the nuclei get larger, they need a greater proportion of neutrons to protons to remain stable. Protons will experience electrostatic repulsion from other protons and will experience attraction due to the strong force from protons and neutrons. Neutrons, however, add strong force to a nucleus without experiencing or providing any electrostatic repulsion. So, why not just have many surplus neutrons? Well, each neutron must be in a different energy state to all the other neutrons in the nucleus. As we add more neutrons, the states for the neutrons are at higher and higher energies. Too many neutrons, and the atom will be unstable due to the high energy states of the neutrons. Stable atoms have found a balance between the electrostatic repulsion, the strong force attracting them, and the neutron energy. So let's go back to this graph called the NZ graph, or neutrons against protons, and the stability curve here. What does this have to do with radioactive decays? Well, if we look at alpha decay, this would reduce the number of neutrons by 2 and reduce the number of protons by 2. So it would move an isotope in this direction on the graph. We find alpha emitters in this region on this graph, and alpha decay would move them towards the curve of stability. Beta minus decay is when a neutron becomes a proton, so it would reduce the neutron number by 1 and increase the proton number by 1, moving an isotope in this direction. We find beta minus emitters in this region, and so beta minus decay would also move them closer to the stability curve. Beta plus decay is when a proton becomes a neutron, so this will reduce the proton number by 1 and increase the neutron number by 1, moving an isotope in this direction. And we find beta plus emitters in this region, where a beta plus decay would again move them closer to the stability curve. So you see, by undergoing alpha or beta decay, isotopes are moving closer to a position of stability. Another way of looking at this is to say that alpha emitters are simply too big. They have 84 or more protons. Beta minus emitters have too many neutrons. And beta plus emitters have too many protons.